Good afternoon. I'm Katherine Blundell, Gresham Professor of Astronomy. The title of my talk today is Cosmic Vision, Fast and Furious. It really is the case that particles that are both fast and furious can inform us about the nature of the physical universe. Up to now, my previous Gresham lectures, the first series on cosmic concepts and this current series on cosmic vision, have focused pretty much exclusively on electromagnetic astronomy. Electromagnetic astronomy is the kind of astronomy that's mediated by rays of light or photons. But what we're going to discuss today is messengers that are fast and furious particles. They go by the name of cosmic rays, but they are not light rays. They are particles that move extremely fast and could do a lot of damage. But first, the weather. I wonder how the comment, "It's always raining," resonates with you. You might think that's just the yelp of a British person complaining about the weather that we had in the first few weeks of 2021. But actually, what I'm talking about here are not raindrops. I'm talking about the energetic particles that are raining down on planet Earth the whole time. Not drops of water at all. When I say it's always raining, I'm precisely talking about cosmic rays. They rain down at the top of the upper atmosphere of Earth, and this gives rise to a cascade of particles lower in energy, spread out over regions of many square kilometers. That's the kind of particle that I'm talking about today. And amazingly, you can do astronomy with these particles. But if it's always raining cosmic rays, how come we don't see these particles all the time? Well, the answer is, actually we do. CCD detectors in modern cameras designed for astronomy capture the evidence of cosmic rays the whole time. Now, you won't see this in most DSLR camera images because typically the exposure times for normal photography are rather short. The vast majority of the photographs I have ever taken have an exposure time shorter than 1/100th of 1 second. In such a short exposure time, you're very unlikely to see a cosmic ray. But the much longer exposure times of astronomical images, and here I mean I routinely use exposure times in excess of 1,000 seconds, mean we are much more likely to capture quite a number of cosmic rays in such images. And that's why when you're trying to make a really good astronomical image of a particular target in the night sky, you'll be wanting to take multiple exposures precisely to remove the effects of such cosmic rays. So this is really important for electromagnetic astronomy. I'm showing here a beautiful nebula in the night sky taken by my friend and colleague Steve Lee. This is an image of the Cat's Paw Nebula, NGC 6334. It's a star-forming region, or I should say several star-forming regions, in the constellation of Scorpius. It was discovered by John Herschel in 1837 at the Cape of Good Hope in South Africa. Its extent from one side to the other is over 300 light years. A light year, remember, is the distance traveled by a ray of light in 1 year, traveling at the speed of light. And what you can see in this image is several regions of ongoing star formation. The image that we're looking at is beautiful, and it is the final product of quite a lot of work and quite a few multiple images. Let me now zoom in on one particular region of this in order to illustrate how we do electromagnetic astronomy without cosmic rays. Although I said at the start of this lecture, we can do astronomy with cosmic rays, and that's really important. What we're doing now with rays of light, cosmic rays are unwelcome. So let me show you what they are and how we get rid of them. So I'm going to zoom in on the highlighted box here. The movie that's now playing is cycling through 3 of the sub-images that went into the resultant image that you saw a moment ago. I hope you can tell that as those images cycle through, you can see little extended wiggles, which are the consequence of a cosmic ray hitting the camera, not necessarily traveling through the optics of the telescope, but potentially incident from all angles, which is why you see funny shapes that don't at all correspond to the points of light coming from starlight. The way that these get removed in order to attain a really high quality, beautiful electromagnetic image are to add these in some way that eliminates the cosmic rays. And one way that we typically do this is to take the median of the input images. So if you've got one image where a few of those pixels have got extremely high values because some highly energetic cosmic ray rocked up and splattered all over the adjacent pixels, when you take the median of a number of sub-images, those high ones will just not play at all, and the median value will be what makes it through into the final resultant image, giving the beautiful example I showed you a couple of slides ago. So cosmic rays are always raining down on Earth. So what are cosmic rays? A cosmic ray is a particle that has mass and very often also has a charge, either negative like an electron or positive like a proton. In fact, a cosmic ray could be a familiar subatomic particle, either a proton or perhaps more generally the nucleus of an atom that has been ionized. Ionized is the word we use to mean that some electrons from a neutral charge, a charge-balanced atom, have been ripped away or excited away because of the energetic conditions that atom finds itself in. So we could be dealing with the nuclei of helium atoms or of iron atoms. But either way, a cosmic ray will be moving very fast. The fact that a cosmic ray is charged is significant, both in terms of the means by which it is accelerated in the first place, and in terms of how a cosmic ray behaves as it propagates through space to get from the site of its original acceleration through to us here on planet Earth. It also makes a difference in terms of how the cosmic ray traverses through Earth's magnetosphere, through the magnetic field that surrounds our planet. More of that later. For now, we'll just note that cosmic rays are moving very fast. We'll see exactly how fast shortly. So the low energy cosmic rays that arrive at Earth actually arise from the sun, or at least from the solar wind, the plasma that our sun is persistently, perpetually giving off. Some of that arrives at Earth and gives rise to the beautiful aurorae that we can sometimes see depending which latitude we're at. Aurorae are streamers of light that can only be easily seen at night, of course, because the sun's light is too bright to give enough contrast for us to see them. The aurorae are also known as the northern lights, or the southern lights, or sometimes the polar lights. That's because you have a greater chance of seeing the aurorae if you're closer to either the North Pole or to the South Pole. They're also sometimes called the curtains to emphasize the folds that you can see in the aurorae. So that's another different from clouds besides the color. What the aurorae actually are is an interaction of the solar wind with the magnetic field that surrounds Earth. More on magnetic fields in just a moment, but the point to note is that magnetic fields change the direction in which charged particles are moving. The solar wind is a plasma that the sun perpetually blows off. It would be wrong to think of this as merely a gas, like the winds that we have here on Earth. A plasma is a very special kind of gas. It's very, very energized, and the charged particles, electrons and protons in the case of hydrogen plasma, have so much energy that the atoms are dissociated into their separate particles. They're ionized into electrons and protons. And those charged particles, that charged particle plasma, when it arrives from the sun to the Earth, interacts with Earth's magnetic fields, and we see these glorious colours. So let's talk a little bit about how cosmic rays behave in the presence of a magnetic field. Magnetic fields aren't completely obvious to understand, but they're great fun and they give rise to some very rich phenomena here on Earth and in the rest of the universe. Let's start with the very simple force due to gravity. Gravity attracts, and the vector is completely obvious if we're on Earth. It's down. The direction in which gravity acts is always along the line that joins the masses in question. But for a particle carrying charge, if that particle is moving at an angle with respect to the lines of the magnetic field, then that charged particle will, in general, follow a helical path, a spiral path around the magnetic field line. So let's consider that we've got an electron that rocks up and it starts moving. The path that the electron will follow is traced out by a helix wrapping around, spiraling around that magnetic field line. The radius of the helix that is thus formed is sometimes referred to as the gyroradius or the Larmor radius. So a key point to appreciate is that if you've got magnetic fields in the presence of moving charged particles, the ways in which those charged particles move will be considerably enriched compared with if the magnetic fields were not there. These spiraling patterns are very important in understanding the behavior of the aurorae and many other magnetic phenomena in outer space. The magnetic field of planet Earth is actually very important for our protection. Without the magnetosphere of Earth, without the magnetic fields that thread the atmosphere of Earth, we would be living on a much more dangerous planet. These magnetic fields protect us from radiation poisoning from the sun, at the same time as giving rise to the glorious phenomena that are the aurorae. Earth's magnetic fields that form its magnetosphere keep us safe from high doses of radiation poisoning. Let's consider for a moment planet Mars. I spoke about Mars in my lecture before Christmas on attentive eyes, and I showed you these images that I had taken last October at a distance of about 60 million kilometres from Mars. It's fair to say that you get a much better view if you're closer to your subject. And here is a picture which NASA released just last week as its Perseverance rover touched down on the surface of planet Mars. This landing was super exciting in terms of the engineering prowess that got it there successfully, but it's also exciting in terms of the exploration of another celestial body. The purpose of the Perseverance rover is mainly astrobiology research. Its goals include the search for signs of ancient microbial life, and we should learn a lot about the planet's geology and past climate. But it's important to appreciate, even though there may or may not turn out to be evidence of ancient microbial life discovered on Mars, we should be under no illusions. It would be very dangerous for us to live on Mars. Mars is hostile for life as we know it because it gets pretty much the full force of the solar wind. Those relatively low energy cosmic rays that arrive from the sun are not pretty much deflected at all until they land on planet Mars. There is no magnetosphere surrounding planet Mars in the way that there is surrounding planet Earth, protecting us from the solar wind. So how were cosmic rays discovered? Well, the discovery of cosmic rays goes back a long time. It massively predates by a few decades the invention of the CCD detector used in astronomical imaging for the images of the Cat's Paw Nebula that I showed you earlier. I'm showing you a cartoon here drawn very kindly by my husband to illustrate an electroscope. When one of these electroscopes is in the vicinity of ionizing radiation, i.e. charged particles, the gold leaves that are shown in the electroscope will be repelled apart. And that's because if both gold leaves are charged up in the same way, say that they're both positively charged, they will want to repel one another. And that is the signature that you have got ionizing radiation present. A slightly more modern day version of a device designed to measure the same kind of thing, the electrometer here, uses metallized quartz fibers, which again repel one another very subtly when they're charged up by the presence of ionizing radiation. And a little microscope or viewer seen just on the left of the electrometer there gives you a sense of how you can view the separation, the repulsion of those metallized quartz fibers. Now, just over a century ago, 110 years ago, Father Theodore Wolff, who was a Jesuit priest, got permission from Monsieur Eiffel, just before the opening of the Eiffel Tower, to take one of these electrometers up to the top of the Eiffel Tower. Father Theodore Wolff measured that there was far more radiation at the top of the Eiffel Tower, which is over 300 meters above the ground, than there is at the bottom of the Eiffel Tower, shown here. So this might suggest that either you get more ionizing radiation high above the ground than you do at ground level, or that there was something rather special about the Eiffel Tower itself, in terms of its ionizing properties, that is, not just the grandeur of its structure. And so, being a good scientist, Father Theodore Wolff actually made the same sort of measurement 300 meters away from the foot of the Eiffel Tower. And again, there was a pretty comparable amount of ionizing radiation compared with the amount that he had detected at the foot of the Eiffel Tower. Again, significantly less than the ionizing radiation which is 300 meters above ground, suggesting that there's some attenuation through those 300 meters of Earth's atmosphere that tends to limit the cosmic rays getting to us here on Earth. Victor Hess used electrometers much like those pioneered by Wolff to take this investigation rather further and rather higher. Hess was an Austrian physicist, and he used balloon flights in order to investigate the presence of ionizing radiation to much higher altitudes, to altitudes of a few kilometers. He made balloon flights himself, often risking his own safety in pursuit of these measurements. And he won the Nobel Prize for the discovery of cosmic rays in 1936. But the person who coined the term cosmic rays is actually Robert Millikan. He's seen here photographed with Albert Einstein. Albert Einstein was awarded the Nobel Prize for his discovery of the photoelectric effect. And that's the effect that led to the idea of light being discrete particles known as photons, particles without mass, it's important to note. Einstein was, of course, very famous for his work on quantum mechanics and special relativity, which we'll be touching on a little later in today's lecture. And he was also famous for his general theory of relativity, which we'll be touching on in the next lecture. Robert Millikan, on the other hand, was the person who really discovered the charge on the electron. Robert Millikan was awarded the Nobel Prize in 1923 for his work measuring electrical charge with his famous oil drop experiment, as well as for work on Einstein's photoelectric effect. Millikan founded Caltech, and as I mentioned, he is the first person to have used the term cosmic rays. Robert Millikan similarly used these electrometers and balloons to make further measurements of cosmic rays throughout the atmosphere as a function of altitude. Very wisely, he used remote balloons, which saves traveling and is greater in terms of personal safety. And Millikan recognized that there must be a source of radiation from space, and that's why he coined the term cosmic rays. He was originally thinking that what was going on was that there were some very energetic photons, but it was later demonstrated that they couldn't possibly be photons. They had to be massive particles that were charged. So Robert Millikan's Nobel Prize came in 1923, and his PhD student, Carl Anderson, shared the Nobel Prize with Victor Hess in 1936. Now let's look more closely at these cosmic rays and consider exactly how energetic they are. It was no accident that I chose the title Fast and Furious for this lecture, because there's an important perspective of the energy of these particles that comes precisely from cricket. Although I have only a hazy appreciation of the rules of cricket, and of course admiration for those whose understanding is better than my own, I do have an appreciation of the laws of physics, and I can work out the kinetic energy of a cricket ball. When a cricket ball is bowled, it goes from being stationary to acquiring kinetic energy, the energy that it has by virtue of its motion. If you take the fastest bowler on the planet, then the kinetic energy that a cricket ball would have is something like 50 joules. It's very straightforward to work out this kinetic energy. 50 joules corresponds to the energy that is in about the most energetic cosmic ray that ever arrives at Earth. But instead of all that energy being in one cricket ball, which weighs something like 150 grams, all of that 50 joules is embodied in just one proton. This is astonishing. If a cosmic ray, let's say a proton, has the energy, which is the same as the kinetic energy of the most rapidly moving cricket ball ever bowled, then that must mean that the speed at which that proton is moving is just huge. And in fact, it's very close to the speed of light. I described in my first Gresham lecture, entitled Faster Than Light, just how fast the speed of light is. We met a unit of distance called a light year. It's how fast a light ray travels in 1 year. It's a long way. It's 1,000 billion kilometers. And so over a distance of 1 light year, one of these ultra-high energy cosmic rays, which is a proton having, say, 50 joules, would only lag a photon by 1/100th of a diameter of human hair. So the most energetic cosmic rays travel very close to the speed of light. As I mentioned, no particle with mass can travel at the speed of light, but an ultra-high energy cosmic ray is not far behind in speed. We're going to continue this theme of Einstein's special theory of relativity now, because it's important for understanding some of the behavior that I'm about to describe for these ultra-high energy cosmic rays. Einstein developed his special theory of relativity in order to explain what happens when things move at speeds comparable with the speed of light in our universe. It's important to realize that special relativity describes physical reality, the actual universe that we live in. Einstein's special relativity says that time and space change in ways that are completely counterintuitive to our classical concepts of space and time for objects that are moving at speeds comparable with the speed of light. In particular, time runs slowly for an object moving so fast, and the measurements of space, i.e. the measurements of distance, are contracted from the perspective of an object moving that fast. Another way of expressing this is that in special relativity, space and time, which become one entity of space-time, become stretchy. A very important equation in special relativity is given by E, the energy, equals this special quantity gamma, which is also known as the Lorentz factor, times mc squared being the famous bit. M is the mass, c is the speed of light. Gamma, this Lorentz factor, is a very special quantity, and it turns out to scale the extent to which time can stretch out and distances can compress or contract in. For an ultra-high energy cosmic ray, such as a proton with this maximum energy of 50 joules, this Lorentz factor gamma will be 10 to the power of 11, in other words, 100 billion. Let's consider a galaxy 100,000 light years across. This means that traveling at sea would take 100,000 years. But because space-time is stretchy, this very rapidly moving proton, this relativistic particle, in its rest frame, would perceive that it would be traveling across the galaxy rather faster. With this particle having a Lorentz factor of 100 billion, then the time of 100,000 years divided by 100 billion would give about 10 seconds. In the proton's rest frame, it would think that the journey across this galaxy, 100,000 light years across, would take only 10 seconds. Well, how could this be reconciled with the distance through space that the proton has to travel? The answer is that in the proton's rest frame, that distance across the galaxy is also contracted. The diameter of the galaxy contracts by that same factor of 100 billion. This is physical reality in our universe, but it only manifests itself at extreme speeds and energies, speeds that are very close to the speed of light. Besides remembering this form of Einstein's famous equation, E equals mc squared, it's important to hold on to the fact that when you describe the special relativistic universe, as I've said, space and time become stretchy, but they do so in ways that depend critically on the value of gamma, this Lorentz factor. Fast and furious then. For a proton, this velocity is absolutely huge. At the risk of labouring how fast the speed of an ultra-high energy cosmic ray moves at, if a cricket ball were to move at the same speed as our 50 joule proton, then the energy of that cricket ball would be equivalent to the amount of energy if you had the entire mass of Australia in TNT, in dynamite. That's an astonishing amount of energy. Incidentally, TNT, dynamite, was invented by one Alfred Nobel, of the prize fame. Alfred Nobel gave many of the proceeds of his development of TNT for these prizes in pursuit of pure science. Now let's consider the origin of cosmic rays. How do they land at Earth, and what do they do when they reach the top of our atmosphere? This drawing is very helpful, I think. Let's imagine that we've got a primary cosmic ray, and that will be a very rapidly moving proton or some heavier nucleon of some description. When it hits some of the molecules in the top of Earth's atmosphere, and obviously the majority component in our atmosphere is nitrogen as N2, then an important reaction happens. A proton and nitrogen together will give rise to pions. Now, pions are not long-lived particles, and these decay into muons. And the muons then travel through Earth's atmosphere, and those are something we can detect at least if we have balloons in appropriate places or detectors on mountaintops. An unmanned balloon can readily and safely reach the height of about 30 kilometers. Concorde, for example, could travel at 15 kilometers. So we really are up in the high atmosphere here. A manned balloon probably wouldn't go above several kilometers, 9 kilometers being where Carl Horster reached in 1914. Just for calibration, Mont Blanc is at nearly 5 kilometers, while Everest is at nearly 9 kilometers. So this is where we're sampling these cosmic rays in the Earth's atmosphere. The arrival of the decay products of the primary cosmic rays that arrive at the upper surface of Earth's atmosphere gives us another illustration of special relativity. And courtesy of another cartoon, thanks to my kind husband, we can consider this example in special relativity. Now, in the laboratory, a muon, which you can think of as being a heavy electron or heavy anti-electron, depending on whether it's negatively charged or positively charged, respectively, has a lifetime only of order 2.2 microseconds. That's very, very short indeed. As I mentioned, cosmic ray muons are produced towards the top of the upper atmosphere when a type of particle called a pion decays. We detect muons at the tops of mountains. So that means for the muons to get from the sites where they are formed when pions decay into muons, they then have to travel a considerable distance to those mountaintops. And the travel time for these muons significantly exceeds the 2.2 microseconds that they typically live for before they then decay into electrons or anti-electrons and neutrinos and so on. How on earth do we reconcile this? In the mountain frame of reference, also known as Earth's frame of reference, we observe that the muons must live for a whole lot longer than the 2.2 microseconds that they live for in the lab. In the frame of the traveling muons, on the other hand, as they are released in the top of the upper atmosphere and then travel towards the mountain, in the muons frame of reference, they see that distance to be contracted. And so here you can see two different sides of the same coin. In Earth's frame of reference, the muons are traveling for vastly longer than the 2.2 microseconds that they live for in their own frames. That 2.2 microseconds is multiplied by the corresponding Lorentz factor gamma, appropriate to the speeds at which the muons are traveling. But in the muons frame of reference, their distance is contracted by the same amount of the value of the Lorentz factor gamma. The existence and the detection of these muons is an illustration of the fact that when an ultra-high energy cosmic ray arrives at the top of Earth's atmosphere from some energetic exotic location in outer space, they create what is known as an extensive air shower. A shower from a single ultra-high energy cosmic ray incident at the top of Earth's atmosphere will have a footprint at the ground of several square kilometers. It depends a little bit on how energetic that cosmic ray is, but if you want to be able to detect these cosmic rays, you need a detector that is very spread out over a bit of planet Earth. I'm going to show you now two examples of modern detectors for cosmic rays. The one on the left depicts the area of coverage for the Pierre Auger Observatory, which is located in Argentina. The Pierre Auger Observatory was proposed by Alan Watson of Leeds and Jim Cronin of Chicago, and its detection area as I say, in Argentina, is the size of Luxembourg. It's named after the Frenchman Pierre Auger for his work on energetic electrons. It's important to realise, in the context of an observatory like the Pierre Auger Observatory, that the Earth's atmosphere is part of the detection instrument itself. By detecting various lower energy particles spread out over a large area of, in this case, Argentina, enables the possibility of backtracking the arrivals of those particles to try and get some sense of where the original ultra-high energy cosmic ray actually came from in space. I'm showing here on the right a second example of a modern day cosmic ray detector. This one is known as the telescope array, and it's located in Utah. Again, its detection area is spread over several kilometers. The fact that you have two such arrays is very important. The Pierre Auger Observatory is important for surveying the southern sky, being located in Argentina. The telescope array in Utah, of course, monitors the northern sky. And there's an area of overlap which can help out with calibrating these extremely difficult measurements. We're now going to consider doing astronomy with cosmic rays. The concept of astronomy with cosmic rays is an important and a fascinating one because it takes us to the sites of extreme energy production in the universe. As I mentioned earlier at the start of my talk, it is very different from doing astronomy with electromagnetic radiation. Astronomy with cosmic rays isn't conventional astronomy in the sense of making images. And this is not because cosmic rays aren't light rays, it's because they're extremely rare. One of the challenges of cosmic ray astronomy is the rarity of the highest energy cosmic rays, the ultra-high energy cosmic rays that I've been referring to. Forget the kind of exposure times that you use for normal optical imaging in astronomy, let alone photography. The rate at which some of the most energetic particles arrive at the top of Earth's atmosphere is something like 1 per square meter per century. And that's why you have to have these vast areas for the detectors in Argentina, in Utah, as I indicated. So what then is the origin of cosmic rays and where do they come from? I want to take you back briefly to some of the objects that I described in my lecture earlier this academic year called Watching the Radio. In that lecture, I described how you could use a spatially distributed network of radio antennas in order to give rise to a particular image. The telescope that I'm showing here is operated by the US National Radio Astronomy Observatory, and it's called the Very Long Baseline Array, or the VLBA. This particular distribution of radio antennas gives a remarkable telephoto lens with much, much finer resolution, finer detail than the Very Large Array radio telescope, which I also spoke about in that lecture. This particular telescope, the VLBA, is a very powerful instrument when it comes to looking at very small, very compact phenomena and those phenomena as they evolve. So an example of this is the expansion of a supernova. Now, some years ago, in 1993, in fact, in the beautiful galaxy of M81, a supernova exploded. A supernova expands very, very rapidly and it can accelerate particles. The expansion speeds that we're talking about for a supernova are initially very fast, getting on for 20,000 kilometers per second. Within a few years, they slow down to something like 8,000 kilometers per second. The actual speed at which they expand can be measured by the VLBA radio telescope shown in my previous slide. And what I'm going to show you now illustrates the successive expansion of the supernova shell at radio wavelengths, starting in 1993 all the way up to 1997 in this particular image. Time is obviously increasing from left to right. Now, the structure coloured red in these images is actually artifactual, so please ignore that. But what's very convincing indeed is how the VLBA has revealed the successive expansion of the supernova shell. And that confirms the expansion speeds that I quoted to you a moment ago. Because supernovae expand so fast into the interstellar medium of their host galaxy, they will cause shocks. And shocks, particularly where you have the presence of magnetic fields, and especially where you have compressed magnetic fields that pervade the interstellar medium, enable the acceleration of particles to very, very high energies. And so if you have galaxies where lots and lots of supernovae take place, we call these starburst galaxies, where there are lots and lots of supernova explosions. And one such example is actually a neighbour of M81 here. It's called M82. It's just across from it in the northern sky. So a starburst galaxy, or many starburst galaxies, are certainly a contributor to the flux of cosmic ray particles that arrive at the top of Earth's atmosphere. But actually, they're insufficient to explain the highest energies of particles that we get, and they're insufficient to explain the numbers of slightly less energetic particles that we get. If you want to think about the kind of locations in outer space where you would expect to be able to accelerate particles to the highest energies, and the energies that I'm talking about are something like 1,000 billion times the most energetic particle that it's possible to accelerate in particle accelerators here on Earth, then you need to factor in something known as the Hillis criterion. The Hillis criterion is named after Michael Hillis, who was a famous professor at Leeds University, who sadly died a couple of years ago. The Hillis criterion says that the maximum energy to which a particle can be accelerated depends principally on three things. These three things are the strength of the magnetic field, and you can hope to enhance that if you can compress the magnetic field, for example, in a shock front. It also depends on the speed at which the plasma is moving through such a shock front, but that tops out at c, the speed of light. So the only other variable which can make a massive difference to the maximum energy that you could hope to accelerate a particle to is the size of the region over which the acceleration can take place. Now, the size of the supernova remnant shell in its entirety, its diameter, in the images that I showed you a couple of slides ago, is actually about a light month. Now, of course, in certain contexts, a light month is an enormous distance, way bigger than the solar system. But in the context of the acceleration of particles up to the highest energies at which we observe the ultra-high energy cosmic rays to be accelerated, a light month is an insufficiently tiny distance over which particle acceleration can take place to attain these highest energies that we actually observe. So size does matter. And so it's prudent to turn to nearby radio galaxies, such as those that I showed in my lecture called Watching the Radio. This is an image that I showed in that lecture of the giant nearby radio galaxy called Centaurus A, shown here for scale with the Moon and the telescope that was used to observe it. This radio galaxy is absolutely huge, never mind one light month for supernova 1993J. Centaurus A is over 1 million light years in extent. In an angular size, that's over 200 times the area of the full Moon. And the large sizes of these radio galaxy lobes allow the Hillis criterion to be met, in principle. But it matters a little bit how the directions of the cosmic rays incident on Earth are determined. Another radio galaxy that we think is responsible for these ultra-high energy cosmic rays is the beautiful radio galaxy Fornax A. So this is several thousand light years in extent. It's not as large as Centaurus A, but there are huge reservoirs in which the acceleration can take place. It turns out that the acceleration of particles to the highest energies does not take place, cannot take place at the most energetic shocks, such as you get in supernovae, like supernova 1993J that I showed you a few slides ago, that these very large lobes in aging radio galaxies that are really quite expanded and really quite flabby and extended are the ideal locations for acceleration of particles to these extremely high energies. It's actually a mistake to look for the most relativistic shocks that you see in much younger and more powerful examples of radio galaxies. These elderly, decaying, faded radio lobes are a much, much more fertile reservoir for the ultra-high energy cosmic rays. So now let me show you a distribution on the sky of where the PA Auger Observatory detected cosmic rays coming from. Let me first make the very obvious point that for this particular projection on the sky, where yellow or light green indicates where you've got the detection of cosmic rays, and blue indicates a much, much lower signal, the arrival of these cosmic rays is not isotropic. In other words, it's very far from being the same in all directions. The region, the smaller region enclosed by those white dashed lines, is inaccessible to the PA Auger Observatory because that corresponds to the northernmost parts of the northern sky, which aren't viewable, aren't accessible from Argentina. But across the rest of the sky, it is absolutely true that you do not have a uniform distribution of the arrival of these cosmic rays. There's a strong yellow peak near the middle, slightly on the right, and then there's a much bigger peak vertically below it in this particular image. My colleagues and I in Oxford, led by Tony Bell, who has pioneered our modern understanding of particle acceleration, especially at shocks, analysed the distribution of cosmic rays and compared them to the locations of Centaurus A and Fornax A, which I've just shown you radio images of. And we think that the correspondence of these extended flabby radio lobes with where there is an enhancement in the detection of these cosmic rays is very encouraging confirmation that these are the sites of the acceleration of the ultra-high energy cosmic rays. The star-forming galaxies, the starburst galaxies that I referred to in the context of supernova 1993J are much more spread out than the two hotspots that I indicated for the detections of cosmic rays from the PA Auger Observatory. Now, you might not think that the agreement is perfect, and it's not. But it's important to keep in mind what I was saying earlier, that charged particles, which many ultra-high energy cosmic rays are, will be deflected by the presence of magnetic fields, either in the intergalactic medium or in Earth's magnetosphere itself, and present deviations away from the original direction where the ultra-high energy cosmic rays were launched. And so we were able to demonstrate that the fading radio lobes of these giant radio galaxies are reservoirs of ultra-high energy cosmic rays. and are a much more likely explanation for the ultra-high energy cosmic rays that arrive at Earth. Starburst galaxies, on the other hand, we demonstrated were insufficient to explain the quantity and the energy of what is observed. These fading radio lobes are ideal reservoirs because they don't have shocks that are themselves too high energy, which are not so good for accelerating the highest energy cosmic rays. These tell us a lot about the nature of the radio lobes in giant radio galaxies. We've been able to piece together the nature of the plasma and the fact that you get backflow, flows of plasma within these lobes, which are precisely themselves responsible for the acceleration of the ultra-high energy cosmic rays, causing, as they do, very weak shocks within these lobes. It's been an absolute delight to study these objects, not just with electromagnetic radiation at radio wavelengths or at X-ray wavelengths, as I indicated in that lecture, Watching the Radio, but also in terms of the plasma processes that are happening themselves. When I'm doing optical astronomy, I despise cosmic rays. I want to do that kind of astronomy without cosmic rays, hence the methodology that I described at the start of my talk. But cosmic rays themselves, and the most energetic examples of these, the fast and furious ones, tell us a lot about the nature of energized plasma that is itself having its origins in the vicinity of black holes, as I described in that Watching the Radio lecture, and as I described in my third Gresham lecture, entitled The End of Matter, is truly remarkable. And these ultra-high energy cosmic rays give us a window into that astrophysical world, thanks to them being fast and furious.